separate derivation. So what happens? Fx is equal to minus x. So then what happens to this? So I have cos omega t and sin omega t. In symmetric interval, sin omega t disappears and cos omega t becomes 2 times 0 to infinity. Right? Yeah? Same thing with this integral also. Okay? So resulting is, so 1, 2 comes from here, another 2 comes from this integral. So 4 by 2 is 2, 2 by pi. Right? This is Fourier cosine transform. Okay? Once again you can get the pairs. Right? Okay, how do you get the pairs? You can put square root of 2 by pi, square root of 2 by pi here and there, right? So transform pairs can be, you can put either 2 by pi completely on the other thing, right? Or here, right? Or separated in both, right? So these transform pairs. So remember, transform is not standalone. Any transform comes with transform and inverse transform. Otherwise, it is useless in a way. So if you transform a function for your, so why do you transform a function? Often so that you can extract information out of this. Okay? But then after doing that you want the original function back. So unless you have the pair, it's useless. Okay? So all transforms generally have to be with the pair. Similarly, sine transform, if you have minus, okay, so similarly you can get the sine omega t. So the factor I is often figured into the transform itself. So following pairs, once again, the sine transform also, you can get the 2 by pi. By now you got it, right? Okay. Okay. So this was the Fourier transform. Okay. You will see the application of this in the afternoon. Okay. And then another transform that will be used a lot during the rest of the course is the Laplace transform. Okay? So Laplace transform I will just briefly define. Okay? Laplace transform of a function, I am denoting it with FL, a Laplace, right? Laplace, and it takes into parameter space of S. Okay? Is defined like this. Okay? So limit alpha tends to infinity 0 to alpha. I don't like to write 0 to infinity directly. Okay? Neither Laplace did. So, why is that? Because this there may be a singularity. Okay? So then you have to evaluate the limit. Okay? So this is a better way of writing the transform. Okay? Often you may have to actually do this in order to get the transform. Okay? All right. Conditions is very important. Okay? Laplace transform actually doesn't have as strict a condition as Fourier transform. For example, it has to be continuous or PWC. Okay, same thing. But this integral need not exist. Okay, this integral actually need not exist. Right? All you have to do is basically ft has to be an exponential order. Okay, so basically this integral has to exist. So if ft is less than equal to some exponential function, okay, with a constant m and some s naught, okay, at all t, okay, then FLS will exist. Then the transform will exist for all s greater than s naught. What does it mean? So let's try putting this back there. Okay, so m is a constant, can come out equal to s naught minus s. So for all s greater than s naught, this function is attenuating. Exponential is minus. Okay? Right? So basically, As long as it's an attenuating function, that integral will be evaluated. Right? Everybody with me? Okay? And even if you are, for some function which is not of that order, okay, for that inverse will never exist. Okay. There are a couple more questions. So this is a simple integral, right? All of you can visualize this. Can you? Yeah? Okay. There is a question. There is a question to you. Red one. You must have got printout of these slides, right? Yeah.
It exists.
Do they exist? Does it exist?
Yes.
Yes. Okay. One yes answer. The answer is no. Why is that?
Square.
It's a square. It's actually exponential. It actually goes to infinity much faster than e to the power minus st can. Okay. It's, after all, what goes to infinity faster? And that's why this condition s greater than s naught. If s is less than s naught, then this will be positive. So it will go to infinity. Net result. So it depends on whether ft goes to infinity faster or this one. Right? So if ft can beat it and goes to infinity, then this integral will not be finite. Okay? Laplace transform would not exist. And e to the power t square goes much faster to infinity than e to the power t multiplied by any constant whatsoever. Right? Okay, for all t, remember? For all t. Right? Okay. So, and because it is an integral, of course, you can see this is an integral operation, so linearity will be always true because integral is a linear operator. Right? Okay. Let me talk about inverse transform a little bit, and because unlike Fourier, in Laplace, you can't really mathematically write the inverse transform. They often have to be, once the transforms are obtained, you often have to separate it out into the known form of transforms of a function and then write that as a function of that, right? You actually have to use a database or table or known table you construct, right? Okay, so basically this is the definition. It has to be one-to-one mapping, okay? But it's not so because of the definition itself. Linearity, of course, okay? Because a transform is linear, inverse is also linear. But is it unique? There is something called an arch theorem. Is anybody familiar with that? Is it unique? Let's go back to the definition. This, right? Yeah? Everybody remembers that? Okay. Is this inverse transform unique? Yes, no. Let me clean up the board in the meantime. Is it unique? Can't say yes, no. Yes, no. If it is yes, why I am asking, right? So that's the good. No. Just let's see. Let us say you have a function e to the power at for which you want a Laplace transform. Let us say Laplace transform exists. Okay. You have another function which is, how does e to the power at look like? Something like this. Yeah. You have another function which has only a finite number of discontinuities. Okay? Function is otherwise, just these are points, these are not even intervals, these are points. Okay? So Laplace transform of this and Laplace transform of this is same. Why? because integration of these two is same. Finite number of point discontinuities have zero area. Right? So inverse transform can map to either this or this. Alright? So ft and gt, okay? So inverse, I mean, they can have the same transform, can have two different inverse transform. Okay? So Lorentz theorem says that if this will, however, always be true, if this is difference is a function, then integral nt dt will be 0. Have to. Okay? So basically, even if there are two functions which actually have the same Laplace transform, when you invert it can go back to either of the two. Right? Okay. But the difference, the integral of the difference has to be 0. Okay? So, I just answered that. I was going to ask you. I asked you actually. Right? So, inverse may not be unique. However, this has to be true. Right? So that's it. Okay? Thank you. You can ask all the questions. I think I have finished in time almost.
Almost.
Yes.
Started a little late.
Question? You can ask me anytime. I'll be around. Okay?